some amount of discipline has to be there with people. So, right. So we are going to start a new topic today because I think I have, in the past few classes, I have discussed a large number of methods of solving problems and equations, and I have given you some exercises to do, which I hope some of you have done. But beyond the point. So really what we are going to discuss is what is in brief called multiple equilibrium. And this is one of the few features where we actually sort of move beyond the usual vision that we have been using of treating what is called as enzymes as essentially catalysts. I mean, till now we have been doing essentially chemical engineering because we have been treating enzyme as catalysts. And I think that because they are of course biological catalysts, but because they are biological, their properties and their complexities are far beyond normal catalysts. And this is something I think we should have a flavor about. I mean, as biological catalysts, they display far more complexity, far more interesting behavior than simple chemical catalysts. Till now, whatever we have been doing, in sense that because we have been doing engineering, we have been treating this as catalysts. And the fact that they are enzymes and they have, and so one of the things that enzymatic catalyst can do is that it can have multiple binding sites. Usually not like this, but the fact that it would be a multimer, and each multimer would have a binding site. So they could be identical binding sites because the enzyme as a protein is a multimer, and if it is on the same polypeptide, then of course even if they are identical binding sites, probably the binding constants might be different. Binding constants may be different, and but here with a oligomeric system which is linked up, these binding constants may actually be the same. Now, the most interesting aspect of this multiple equilibrium, which is why we are talking about this, is that the binding of one on one of these oligomers, and that is where enzymes are catalysts which are far more complex than other catalysts. The binding of one actually changes the binding of the other. And the binding of two then changes the binding of the third. And the binding of three then changes the binding on the fourth. And this, even though otherwise they have same binding constants, and this change in binding is actually referred to as cooperativity. Right? So the binding, and these are the ligands, and so the ligands, when they bind, and so cooperativity refers to the very simple point that a given ligand affects, binding of a ligand affects subsequent effects. I mean, remember that cooperativity and therefore allostery, that you would have heard of allosteric enzyme, where this binding regulates the binding of other, it has an overlapping but different meaning altogether. Allostery and cooperativity are different. You could have an enzyme which is cooperative but not allosteric, and you can have an allosteric enzyme which is not cooperative. But usually allostericity and cooperativity are seen in the same systems, and that is why we talk of them as in the same breath. But we have to sort of understand that they're actually different concepts. Cooperativity simply means the binding of a ligand to a particular site here will impact on the binding of ligands in the subsequent multi-site enzyme. Multi-site enzyme usually could mean that this is not necessarily a monomer but a multimeric enzyme. So usually we talk of multimeric enzyme, and if the same ligand is being talked about, we obviously call it homotropic effects. Homotrophic effects, And if there are different enzymes, then we talk about heterotrophic effects. And I will not talk of heterotrophic effects. Essentially, heterotrophic effects is very, very similar to allosteric effects, especially when they have regulatory roles to play. So cooperativity with, and it is very important that there are homotrophic effects. And this is the reason, I mean, and the fact that enzymes show homotrophic effects, binding of one affects the binding of the other, is the reason why all of us are alive and not dead, right? I mean, you have to understand that we are all alive because enzymes have the ability to show homotrophic effects, because hemoglobin is the best example of such cooperative effects. And this ability to bind and to release, oxygen is one of the most important parameters which impact on life. So, and I am sure you've heard of hemoglobin and you've heard of the Hill equation. Have all of you heard of the Hill equation?
Yes, sir.
In biochemistry? Now, what is the Hill equation? Vmax S raised to of n Km plus S raised to of n. You're familiar with this equation, Hill equation?
Yes, sir.
So basically, it also is derived essentially from this basic argument that E binds with n substrate molecules to give ES. Okay, and so the association constant or the dissociation constant or the association constant, let us say. So I'm making a simple, the association constant is essentially given by, please go ahead. Sorry, I like Ka. I like K association. Association constant is E into S association upon E into S S of n. Right? And so now we can find out ES by the same way that we did ES by E total. What is it equal to? Please go ahead. Tell me. What is ES? ES is KE raised of ES by E total. I just wanted to tell me what is E total. E total is, I hope, well, let me write it for you. E plus ES, free enzyme plus bound enzyme, right? Please go ahead. What is ES equal to? What is the fractional saturation that we talked about in this case? What is the fractional saturation here? ES is equal to, or we can reverse it and write 1 upon Ka. Okay, let us, sorry, I should have done it like that. KD is equal to E S S of n upon ES. So if KD is equal to E raised of n, upon ES, and ET is equal to E plus ES, then what is ES upon ET? In the same way as we did everything else. So ES is equal to, E into S raised of n by KD, right? Let me sort of rub this out. Okay, don't need to rub it out. ES is equal to, okay, upon ET. What is ET? E plus ES, which is E S S of n by KD, right? So we can take E out of this expression, and so what do we get? And multiply by KD. What do we get? ES by ET equal to the fractional saturation. The fractional saturation, I'll write it here. Fractional saturation, which is this term here, is equal to S S of n upon KD plus S plus. Right? And so we can see that this expression can be derived. Right? So this is the Hill equation, where KD is the dissociation constant and uh, uh, and this is the expression. Now, why is this important? Because we can see that when you change substrate concentrations, and the graph of this equation, first of all, let us plot this out. So this equation is important because this generates the so-called interesting sigmoidal graph. I mean, okay, sorry. This generates the so-called sigmoidal graph. So normal enzyme kinetics is like this, but this enzyme kinetics is like this. And the degree of sigmoidity, whether it is very, very highly sigmoid or less sigmoid, etc., will be dependent on the value of n. So you can see that for what is the half of the maximum velocity for this? What is V half? When is V is equal to V by V half? So what do we write it as? If this is Km, or V, as a matter of fact, is Kd. So when is V equal to V half? So we get V by V max is equal to half, okay, is equal to S star of n upon Kd plus S star of n. Right? So what does this tell you? Kd is equal to S star of n. So when Kd is equal to S star of n, so actually therefore S becomes nth root of, Kd raised to n by n. Right? And so many times people write this Kd as, just for convenience sake, so that it's half maximum velocity at kh, we write it as kh raised to n. So many people in biochemistry textbook, sometimes you will see V is equal to V max S star of n upon kh raised to n plus S star of n, where kh is half maximum velocity in the sense that we use km, where when s is equal to kh, V is equal to half V max. Sorry. So when V is equal to half of V max. So therefore, many people write it like this, just for a easy representation or familiar representation of the Michaelis-Menten kinetics. And obviously, we can simplify this, or the basic purpose, I hope you realize, is the concept of elasticity. The basic purpose is that this response is very, very fast. You can see that this response here is very, very fast. For example, when let us do some problems. I think we should first do problems. Otherwise, there's no point teaching theory without solving problems. For example, what is the amount when we have a normal equation, and let us take n is equal to 4, which it is not, but still, let us take n is equal to 4. So we have V is equal to V max S raised to 4 upon Kd. I will write it Kd plus S raised to 4. And we also compare it with normal V max S upon Km plus S. Now, suppose I say that I want to increase the velocity from, say, 10% of V max to 90% of V max. Or you can take 20% or 80%, whatever. I'm just sort of saying. Now, what is the amount of substrate concentration that needs to be increased here, and the amount of substrate concentration that needs to be increased here? So, can you tell me the answer for this one at least, first one? So, what is the S when V is 10% of V max?
Sir, in terms of Km.
Obviously it has to be in terms of km. तो
yes.
मतलब but actually जब आप multiplication करेंगे तो आपको सीधा आंसर मिल जाएगा ना. It really does not matter. तो v is equal to
1 by 9 okay.
v by vn 0.1 is equal to s upon km plus s. So km is equal to
Sir, s is equals to 1 by 9 km.
1 by 9 km.
Yes, sir.
And when we want to make it 0.9, 90%.
9 by 1.
Yeah, so s becomes equal to 9 km. 9 by 1.
Yes,
ठीक है ना? And therefore the increase in s, fold increase, is 81 times. So you need to increase it 81 times for it to go from 10% to 90%. 81 times increase of substrate. So you need to increase substrate quite dramatically if you want to increase the velocity. Now let us look at this fellow here with a power raised to 4. कितना fold increase करना पड़ेगा? So again, 0.1 is s raised to 4 upon kd plus s raised to 4. तो क्या हुआ ये? और अगर आप चाहते हैं तो इसको kh raised to 4 लिख लीजिए, just for convenience. अब थोड़ा डिफिकल्ट है, थोड़ा सा माइनर अलजेब्रा here. Please go ahead. So this is the purpose here. How do we achieve this? So you will discover what is it? How many fold? ये बहुत मुश्किल तो नहीं होना चाहिए.
Sir, 1 by 9 kd की power 1 by 4.
हाँ ठीक है. भाई आंसर मुझे लगा ऑब्वियस है. 81 रेशो 1 by 4 टाइम्स. इसमें 81 है तो इसमें 81 रेशो 1 by 4 टाइम्स होगा, क्योंकि s जो है वो मतलब s अगर इंक्रीज करेगा s रेशो 4 कितना, ये अगर s रेशो 4 को मैं सम a ले लेता हूं, इतना कॉम्प्लिकेटेड करने की क्या जरूरत है. अगर मैं s रेशो 4 को a ले लेता हूं तो a हैज टू इंक्रीज 81 टाइम्स. सो s हैज टू इंक्रीज 81 रेशो 1 upon 4, which is 3 times. 3 into 3 into 3 into 3. ठीक है ना?
Yes, sir.
भाई ये अभी अपने आंसर निकाला था 81 टाइम्स, तो मुझे लगा कि ऑब्वियस है ना. 81 टाइम्स रेशो 1 by 4 है ना, बिकॉज s रेशो 4 हैज टू इंक्रीज 81 टाइम्स, तो s हैज टू इंक्रीज 3 टाइम्स, right? So therefore this has to increase 3 times only to go from 10% to 90%. So obviously you can see that there is the advantage of the power, so the more the power, the more easy it is, right? So therefore we need to understand this, but I want to explain this in terms of more sort of complex concepts, and I don't want to keep it simple, and we can talk about so first of all, let us now sort of go back to, this was just an example of Hill equation, and this was a simple understanding, but we now need to sort of understand multiple equilibria in a more, I mean, I think we have a couple of lectures available. I could have jumped that part, but I think it is important for you to understand some a bit more detail of multiple equilibria. So we will begin with the basic concept of multiple equilibria, because there are certain concepts that are important here, and let us go through it very slowly. So let us sort of begin by, I mean, essentially we are talking about multiple binding sites, and they're all, let us begin with identical binding sites. Let us begin with the simple problem of identical. Sorry. Identical binding sites. binding sites. And let us, I mean, something which we did not do actually. See, remember E plus A is EA, right? Right. But, and we always talked about EA bound, but we forgot that, you see, and this is very important, S, and that's why I'm calling it A here. Now, S was far in excess, S naught was far in excess of ET. And therefore, there was always, see, S, this EA or A here, the substrate, if it is not in far in excess, this EA bound, so therefore A bound or the substrate bound substrate is going to impact on the total substrate ST. But we always solved it for S in excess, right? We never solved that, but I think it is important now. And this assumption was because we were working with catalysts. But when we are working with multiple equilibrium models, or for example, Eddie Hofstee, or as a biochemist, often we use very large amounts of enzyme and substrate almost in the equimolar concentrations, in which case the assumption that A is in excess is no longer valid. And remember that A bound is what? A bound is simply equal to EA, right? In terms of molar concentrations, is equal to EA, right? So what is EA equal to? A bound equal to? Deliberately I'm writing A instead of S so that it does not create the same confusion, because S, whenever we are working with, we make this assumption, which we don't want to make here. So what is A bound equal to? EA. So same way, exactly, the EA is just the fractional saturation total amount, right? So it is equal to, come on, E naught A upon KD plus, I mean, are you following this? KD plus A. Hello. And let us, or we can do it slowly. Okay, I mean, let me write it out. I hope you're following. E naught is equal to E plus EA, right? And A naught is equal to A plus EA, right? Instead of, see, earlier we assumed that this EA is much smaller, so A is equal to A naught. So what is A bound equal to? Is this all right? Or is it not clear? I sort of wrote it just straight away, because just the same way we discovered. And remember that there's a bound amount. This is the free, this is the free, this is the free, and this is the free. And the bound is nothing but EA itself. Okay, if you are not replying, I assume it's all right.
Yes, sir. Yes, sir. सर एक चीज कहनी थी.
हाँ.
सर अब बस 2 क्लासेस और रहती हैं सर इसके अलावा.
हाँ. हाँ.
तो बस ये बताना चाहिए.
हाँ, तो ये 2 लेक्चर्स हैं, इसमें मैं आप लोगों को पूरा मल्टीपल इक्विलिब्रियम और वेरियस मॉडल्स खत्म करके मैं इसको रैप अप करूंगा बस, है ना. वी आर एज अ मैटर ऑफ फैक्ट आई विल ट्राई टू रैप इट अप. ओह माय गॉड, आई एम गोइंग वेरी स्लोली. नो, बट लेट अस गो स्लोली. आई प्रेफर टू गो स्लोली रादर देन.
हां सर, वो फिर
आप लोगों को समझने में दिक्कत होगी. हाँ, तो अगर मल्टीपल पॉइंट्स होंगे तो ये ई नॉट में हर एक ई नॉट के पास n साइड्स हैं, तो A बाउंड क्या हो जाएगा? इक्वल टू n E naught. Let me call it actually F. चलो ठीक है. F is the number of sites, but the number of sites is n into E naught. N into E naught is equal to, because अब मैं इसको F naught लिखना चाहिए था मुझे actually, so that F naught represents not the number of enzymes but the number of enzyme sites, because now enzymes can have, one enzyme can have more than one site. So अगर 1 molar मतलब 0.1 मिलीमोलर एंजाइम है तो ऑब्वियसली 0.1 मिलीमोलर इक्विवेलेंट साइट्स नहीं होंगे, मतलब इनटू द एवोगाड्रो नंबर, बट इट विल बी इनटू n. सो ये एक्चुअली ये गलत है. ई नॉट की जगह n ई नॉट होगा इनटू a upon Kd plus A, right? So A bound will be N E naught A upon Kd plus A. And now the number of binding sites is number of binding sites. But if there is a much more important point that you are that must be considered, which because you cannot equate A naught, the A bound, with EA anymore. You understand? This we have assumed equal to EA. But when there are multiple binding sites, this is no longer possible. Why? Because, please remember, and that is why this is conceptual rather than arithmetic. So, A bound, what is A bound equal to? A bound is equal to EA, the amount bound with enzyme A, plus 2 into EA2. Because this enzyme is carrying, so some enzymes, one enzyme is carrying A bound at one site alone, some enzymes. Some other molecules of enzymes are carrying 2 bound molecules. Some other, it is not that all of them are carrying 4 or none at all. These are carrying 3 and some are carrying 4. So this EA is obviously carrying this EA. This EA is carrying only one. This one. This fellow is EA. But this is EA2 carrying 2 A's. And this is EA3. So it is plus 3A3. Right? And till plus N EAN. Sorry, EAN, right? So EAN is carrying N molecules. So the bound A is distributed between enzymes, and this enzyme itself is in different forms. It is a single, some enzymes are completely free. There's a free enzyme. Some enzymes are carrying 1, some enzymes are carrying 2, some enzymes are carrying 3, some enzymes are carrying 4, and so on and so forth. So the bound A is given by this expression here. Is this clear? So now we have basically multiple equilibrium relationships. I will sort of wipe this out. And I'm sort of trying to increase more and more complexity here slowly. So you have to please remember that the E plus A, right, is EA. And we have a dissociation constant, let me call it K1, right, as E into A upon EA, right? But we have also EA plus A dissociating into EA2, right? And we have K2 equal to EA into A. Somebody has to put their mic off, please. Upon EA2. Do you follow this? And we have EA2 plus A going to EA3, where K3 is equal to, please go ahead. Hello? Somebody should talk now. EA2 into A upon EA3. Is this all right? Yes. And so till N, EA N minus 1 plus A giving EAN, and you can write the equation as well. Now each step has its own dissociation constant. Now, each of these steps has different dissociation constants. E binding to A might be different from EA binding to A, and EA2 binding to A, EAN minus 1 binding to A. Each of these are called the macroscopic dissociation constants. And we can solve it. And we will solve it. Okay, but before I solve it, before I solve it, I should tell you that even this description is not accurate. So we will come back and solve it, but we will divert from some time here and say that these are called the macroscopic binding constants. But the true way of looking at this is even more interesting and complex, but it leads to better insights, which are called microscopic binding constants. And for some time, let me sort of deviate. We will come back to this and derive this in the next class. Microscopic binding constants is what I want to talk about. And I hope a little bit of tedious algebra should not bother you too much. Okay, so these are the macroscopic binding constants, and we now want to look at the microscopic binding constants. What is this? Okay, and we want to look at the derivation of the general binding equation in terms of this. So let us sort of start this quickly, and this is what I was sort of leading up to because I want to wrap this up quickly. So essentially, I'm saying that, I mean, essentially you are all clear now. E and then plus A, I should write it, minus A is EA, and then again, which is a macroscopic binding constant of K1, and then EA plus A minus A. I hope you're following this. This is sort of separate, sorry. Plus A minus A, and this is EA2. Oh, EA2, and this has a binding constant K2, right? And EA3 and so on and so forth. I hope you're following this. Plus A minus A, and this is EA3. This is these are the macroscopic binding parameters, K1, K2, K3. But really, if you want to understand it properly, this is not the way it is happening. Suppose there are three sides. Now we have E here, and it has, say, 1, 2, 3, three binding constants. Now, who is to say that EA represents EA or EA or EA? You understand? I mean, 1, 2, 3 position में यहाँ लगा दिया, just for you to understand this. So EA can be generated in three ways, and each of these is the real microscopic binding constant, which I will use with a small k, K1, K2 and K3. Of course, ये reverse भी है ना? So the microscopic binding constants K1, K2, K3 really tell you for three sides that there are three ways in which E can bind to the A. It can bind at the site 1, site 2, site 3. And we are, as I said, right now we are taking them as equal. And then EA here can become, it can become E whatever, Can you tell me what it can become? It can become EAA, and it can become some EAA. So this binding constant, and I mean reverse में draw करते करते परेशान हो जाऊंगा. This is EA. So this is K13, and this is K12 is the binding constant. Are you following this? Similarly, this fellow here can go to here. And what is this? This is K2. No, it cannot go here. It can. This is A and A. So this is not there at all. This can go here. Right? And you can see that this is K21 instead of K1. Both of them have reached this 1 and 2 sites occupied, but this is K12 and this is K21. Or maybe I should have drawn it like that. So hold on just a minute. That will make the drawing much simpler. So let me sort of draw this as 1, 2, and this as 1, 2, and daughter is 1, 3, and this is 1, 3, right? And then this can go here, and this can become K21. Okay, and then of course this fellow can also go to another option here, this here. So K3, and so can you see this argument here building up?
Yes,
So
sir.
this can go to these two places. This fellow can go to two places. So K2 can go to K21 and it can get to K23. K3 can go to K31, sorry, ulta, K31 and K32. And K1 of course could run K12 and K21. And then of course all this can go by K1, 2, 3 to the all three sites occupied. No, A, and all these three sites occupied, right, with A's. And 2-1 can go to 2-1-3, and 1-3 can go to 1-3-2, and so on and so forth. So I'm labeling these microscopic binding constants as with one, the first letter being where the site. Suppose there are three sites in the enzyme molecule. Site 1, site 2, and site 3. So this is 1, this is 2, this is 3. The order in which it binds, so these are the true microscopic binding parameters. K1, K2, K3, K12, K21. Okay, and K13. So each of these has three options first, K1, K2, K3. Then K1 has two options, K13 and K23. K2 has two options, K23 and K21. K3 has two options, K31 and K32. And then all of these have one more option leading to all three. So you have multiple situations, but the triple bound enzyme, this EA3 as it were, is arrived at by three different mechanisms. By K123, by K213, and by this. These three options are leading up to this exam methodologies. So this is the method by where first one binds, and the second one bound, and the third one bound. This one was the second one bound first, then the first one bound, and then the third one bound. And the third one is 3-2-1, where the third bound, and then the second bound, and then the first bound. So these are the microscopic binding constants, and they are now can be used to derive the macroscopic binding parameters that we are talking about. Is this argument clear pictorially?
Yes, sir.
So now let us look at each one of them. So can you rub this out? Let us look at each of these separately and understand how these microscopic binding parameters can lead to macroscopic binding parameters. Now we talked about K1, capital K. We talked about capital K1. Let us say capital K1, and what was that equal to? It was equal to EA upon, E into A, dissociation constant liya tha, E into A upon EA, right? But this is actually equal to E into A upon E A plus E A plus A E, है ना? Or I would call it EA1, EA2, EA3. Is this clear? There are these three A's, bound here, bound here. These are all the bound. So the EA, this EA bound, is a sum of three bounds which are bound at different points. So EA is not just EA a single whole. It is EA plus EA plus EA. Right? And the microscopic binding parameters, the small k values, the K1 is now equal to E into A upon EA. Right? So and K2 is equal to E into A upon EA. मैं मतलब पोजीशन शिफ्ट कर रहा हूं सिर्फ. And K3 is equal to E into A upon EA. A यहाँ पे बना हुआ है. These are the different bound forms, 1, 2, 3 forms, right? And therefore we can sort of write EA, this fellow here, EA as equal to EA by K1, and then this fellow here EA as EA by K2, and so on and so forth, right? And this fellow EA equal to as EA by K3. And obviously we have to sum all these three. तो क्या होगा भाई बताइए? This simple Ohm's law, parallel. So EA क्या है?
EA upon K1.
हाँ, तो EA upon K1, तो EA कॉमन ले लीजिए तो क्या हो जाएगा ये? is equal to E into A upon EA कॉमन ले लीजिए.
Then it will be 1 upon K1 plus 1 upon K2 plus 1 upon K3.
On K3. So therefore, can you see that now I will, that much I can jump, I'm sure. So can you now see therefore that, sorry, थोड़ा मिटाता हूं मैं ये, तो इसको तो मिटा सकता हूं, है ना? And so therefore you can see very clearly that 1 upon K is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3. Right? K1. So the macroscopic binding constant K1 is related to the microscopic binding parameters by this basic equation. Ohm's law इसलिए मैं कह रहा था. ठीक है ना? Okay, all of you can follow this. And obviously, if the microscopic binding parameters were all constant, if K1 is equal to K2 is equal to K3, then what do we have? If they are all equal, then what do we have? Then K1 ये 3 by K1 हो जाएगा ना फिर ये. Sorry, K, small k. I'll just write it as 3 by small k because they're all equal to K. So small K1 because K1, है ना? So therefore K1 is equal to K1 by 3. ठीक है ना? Is this all right?
Yes, sir.
Now let us come to the second one. अब दूसरे पे आते हैं. अब ये थोड़ा, this is slightly more irritating, but I'm just sort of wanting to do this slowly because I don't want it to. Well, later on, when these binding constants impact on each other, then the models become more complicated. Now, what is the second one? Second binding step, K2. So you have to remember that, I hope you realize this, K2, the K2 macroscopic parameter is equal to EA into A, right, upon EA2.
EA2.
Right, but now this is now equal to what? This is E. Oh. This EA is now composed of 3 parts. EA plus EA plus EA, right, into A, and EA2 is also composed of various combinations. EAA plus EAA plus AA. Okay, so there are 3 combinations possible. EAA, so 2 sides, either 1, 2 can be occupied, 1, 3 can be occupied, and 2, 3 can be occupied. So this is your K2.
Yes.
And now
Yes,
remember that K12. Now remember K12 was equal to EA upon E12 है ना, तो ये वाला होगा AA, right? And K13 is equal to, and so on and so forth. Can you remember this?
yes, sir.
So
Yes.
therefore EAA, this tells me that EAA is equal to EA into A upon K12. And so we can find out K12, K13, K23, and so on and so forth. Can you now see what I'm trying to do quickly?
Yes, sir.
So now we have EA. Sorry. So we have now these three parameters, and I'm sort of quickly going to write this out for you people, because so can you now derive this basic expression K2 is equal to, now I don't know whether it's making sense or not, K13 what will it be, K21, am I doing right, K21, K23 plus K12, K13, K23. Am I looking it right? No, I'm doing it 3-2 आना चाहिए था. Sorry, क्या कर रहा हूँ मैं? Actually, see the problem is I'm trying to jump too many steps here and trying to do it mentally. It's not possible. I think we'll have to handle it in the next class. Plus K13. At least the denominator you can find out much more easily. So let me forget the numerator. Let me sort of do the denominator here. Can you tell me what is the into A है ना ये? तो वो, that is why it is causing more issues. Can you tell me what is the denominator? First, let me not do it so quickly. Let me do it slowly. So EAA, EAB. So can you? So can you see the combinations here? What are the combinations here? K1. There are 2, K13, K,
2, 3.
and we will reverse it later on. K2, 2-1, K3-1, K23, K32. Actually, I should have drawn it much simpler. Can you see 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. These are the 6 parameters here. Can you see this?
Yes, sir.
And by symmetry principles, and I will not sort of do this, but I think I will just sort of let you calculate it. Otherwise, in the next class, we will do it tomorrow. Can you see this basic expression? By symmetry principles, I will be able to derive K2 equal to actually combinations of 3s. So pick NC3, this into this into this, and the niche wala combination of 2s. Basically, we will get K12, K13, then K13, K12, I think I'm just causing more confusion trying to short circuit this, but it will be 3 combinations let me sort of actually let me not do this here. Let me sort of leave this for you people to think, because I think I would rather, I was trying to do the short circuit. Let us not do the short circuit. Let us actually write it for you people and leave it at that point. So as I said, let me sort of, these are the binding constants. I wrote very clearly what were the three values. K2, sorry, small K2 is equal to EA, sorry, this is capital K2, EA into A upon EA2, which was equal to EA, sorry, EA plus EA plus, plus EA into A upon, same thing, EA2 here. So EAA plus EAA plus E, these two, and then AA, right? And we said we can now say K12 small k. Now this was capital K here, and small K12 is equal to EA into A, of course, upon EA2 as far as we are concerned, and small and then this of course tells me that this is K1 to remember. So this tells me that EAA is equal to EA into A upon K12. Right? And similarly, we have to sort of derive the other expressions. So all these expressions have to be now derived. 1, 2, 3, 4, 5, 6. So we will get EA. So this is the three sums. So now what is this equal to? So now look at this one. This one is equal to, let us sort of just, I'll do the lower one, that is why I said. This one here is equal to EA into A upon K12. This one here is equal to EA into A upon K13, and so on and so forth. And then again EA has to be now broken down into component parts from K1 and K2. Are you getting my argument? Not really. Anyway, it's 10 o'clock. Let us stop here. I think I was trying to short circuit this, and I think it is going to cause confusion. So we have to be able to derive K2 in terms of its component parts, the various microscopic binding constants, and you have to derive K2 from these binding constants. And this algebra is important. Let us stop here, and next class we will resolve this algebra, and then we will try to finish the models based on this concept. Thank you. Any questions? I'm sorry, the power went off. And I think we will stop this recording.